Welcome to this month's BA Wednesday webinar. As usual, we're running the webinar on Zoom with a live stream to YouTube, and the recording will be available to watch on our YouTube channel afterwards. You can ask questions by typing into the Q&A on Zoom or in the comments on YouTube, and we'll answer them at the end of the presentation. It's my pleasure to now hand over to Roger Dymock, the Assistant Director for Exoplanets at the BAA Asteroids and Remote Planets section. Over to you, Roger.
Well, good morning or good evening or good afternoon all, depending on which part of this planet you happen to be sitting on at the moment. This presentation is in 4 parts. It's a brief introduction to exoplanets, projects in which the Exoplanet division has been participating in for some time, our new Microlensing project, and other possible projects that may come down the tube. So an exoplanet primer. Professional astronomers are moving from an age of discovering exoplanets. Transit photometry is one method of doing this. Just get my laser pointer up. Transit photometry is one method of doing this, to characterization. For example, the measurement of the mass, radius, and orbital inclination, which can find the density and possible structure of a planet. So you've got planetary mass along the bottom here and planetary radius up the top, and you can roughly get some idea of whether it's a gaseous planet or a rocky planet. But you'll notice these error bars are rather large, so it's not an exact science at the moment. Another thing that's key is the search for biomarkers in the atmosphere, which might indicate the presence of life. This is done by spectroscopy. The ultimate aim is to answer the question, is there life elsewhere? Whether this infamous Martian worm found in a meteorite in Antarctica is an example of this is still an open question. The Exoplanet division is involved with 2 space missions that will be characterizing exoplanets, ARIEL and Plasto, but more on these later. Finding Earth-like planets in the habitable zone, that's this area here, of sun-like stars, that's us along here, is therefore key to answering the question, is there life elsewhere? The habitable zone is the orbital region around the star in which an Earth-like planet can possess liquid water on its surface and possibly support life. And liquid water is essential to all life on Earth, and so the definition of a habitable zone is based on the hypothesis that extraterrestrial life would share this requirement. The habitable zones for various classes of stars are shown here. In this hot area, planets in this zone are close to their host star. For the solar system, this will be where Mercury and Venus reside. The warm zone, that's fortunately where we sit, and the cold zone, exterior to the habitable zone, is where Mars and the giant planets reside. Planets to the left of this dashed line are tidally locked and always present the same face to their host star as the Moon does to Earth. Thus, life as we know it might find it difficult to survive on planets in the habitable zone of red dwarfs, K and M type stars, which can be very active. Everyone wants to find an Earth-like planet in the habitable zone of their host star, but few have been discovered. This slide shows exoplanets classified by their size along here and the zone which they inhabit, the hot zone, the habitable zone, and the cold zone. The number of exoplanets with accurate measurements of mass is small, as I mentioned earlier, and therefore this chart should not be considered to be set in stone, but it does show how varied exoplanets are. The habitable exoplanet catalogue lists only 1, possibly 5 Earth-sized planets in the habitable zone of a sun-like star. However, considering the number of G-type stars in the Milky Way, the likely occurrence of Earth-like planets around them, there have been many more awaiting discovery. Watch this space. There are 4 ways of discovering exoplanets, and more recently a 5th and 6th have been added. Top left is the radial velocity method. Planets and their host stars orbit around the center of mass of the system, and thus a large planet will cause a change in the position of the host star. This is detectable by very accurate spectroscopy, measuring the red and blue shift as the star moves away and towards us. Best left to the professionals, but there is one instance where amateurs have done that. Direct imaging has been achieved using very large telescopes. Again, job for the professionals. Top middle, this one, transit photometry. If a planet crosses the face of its host star as seen from Earth, then measuring the drop in magnitude of the host star is well within the grasp of amateurs, and many do this at the moment. Detection of exoplanets by gravitational lensing will be enlarged upon in the 3rd part of this talk. 2 more methods have recently come to light. Radio waves from red dwarfs may originate from interaction with exoplanets. The video on the next slide will explain this. And bottom right, a dip in an X-ray signal may be caused by a transiting exoplanet. Possible such detection in galaxy M51. So we've got a couple of videos to follow, both about 3 minutes each.
The Northern Lights, or Aurora Borealis, are one of the most impressive natural phenomena on this planet. Now, astronomers from Astron, together with teams based at other institutes, have detected radio waves from a star intimately connected to auroras, which means that there must be an exoplanet there. For this, they observed radio waves at the Low Frequency Array, a giant radio telescope consisting of around 20,000 connected antennas spread all over Europe. On the 16th of June 2016, the astronomers spotted an intriguing signal coming from GJ 1151, an ordinary red dwarf star 26 light-years from Earth in the Ursa's major constellation. Stars emit all kinds of electromagnetic waves, but these low frequencies have not been closely studied before. After crossing off many possibilities, the researchers found that there was only one explanation. The signal was being produced by an interaction between a red dwarf star and a planet. This discovery is reminiscent of a mystery from our own solar system in the 1960s. Jupiter is emitting radio waves in sync with the orbit of one of its moons, the volcanic Io. But why? It took a decade of observations, as well as visits by the Voyager and Galileo probes, to find out. The constant volcanic eruptions give Io an atmosphere, and radiation knocks atoms into charged electrons and ions. This means that Io's atmosphere is conducting electricity, while it moves through Jupiter's strong magnetic field. An electrical conductor moving through a magnetic field causes a voltage to build up. The voltage pushes electrons to move along the magnetic lines, spiraling around them and emitting radio waves along the way. For the most part of the journey, the radio signal is weak, but close to the star, the magnetic field lines get more crowded, and the spiraling electrons start to feel each other. They interact more and more, emitting strong radio waves in unison to create a radio wave laser beam. As Io circles Jupiter, this beam will hit the Earth from time to time. Mystery solved. The very same thing seems to be happening on a much larger scale, but this time it is the red dwarf that is providing the magnetic field. Electrons streaming between a planet and GJ 1151 will produce radio waves like those that have been measured. Now, this still has to be confirmed. If there is truly a planet, the waves will switch on as the radiation beam crosses the Earth, and off when it passes. The researchers are now checking other nearby stars and expect to find dozens more with similar radio waves. This method could provide a new way to discover exoplanets using LOFAR and future radio telescopes such as the Square Kilometre Array. And regarding those auroras, electrons eventually fall down into the star and crash into its outer layers, causing the shimmering curtains of aurora. Only in this case, they shine over a star instead of a planet, and may even be visible to telescopes on Earth. And if the newly discovered exoplanet has a magnetic field, like the Earth does, the same thing is bound to happen on the other end. This would cause auroras over an exoplanet, including the accompanying radio waves. We may even detect those. The hunt for exo-auroras is now in full force.
Second video, 3 minutes, this one.
And Roger, just before you move on to that, we had a comment that the sound is very low volume.
Okay, let me have a look, see what we've got over.
So I'd look at your Zoom settings. So now try pressing to continue. There you go.
Right, yeah, okay. Learn something new.
Astronomers have announced that they have found evidence for the first possible planet discovered outside of our Milky Way galaxy. To do this, they used a technique looking for the temporary dimming of X-rays from an object with NASA's Cuevas Observatory. This intriguing result could open up a new window for exploring exoplanets, that is, planets outside our solar system at greater distances than ever before. Until now, astronomers have found all known exoplanets, defined as planets outside of our solar system, and exoplanet candidates in the Milky Way galaxy. Most of these have been less than about 3,000 light years from Earth. This new Chandra study looks at a system in the Messier 51, or M51 galaxy. This galaxy is nicknamed the Whirlpool Galaxy because of its spiral shape. It is located about 28 million light years from Earth. One system in M51 in particular got the attention of a research team. This system, known as M51 ULS1, belongs to a class of objects that astronomers call X-ray binaries. In these systems, a massive star is in orbit around either a neutron star or a black hole. Because the neutron star or black hole has such a strong gravitational force, it pulls material from the companion star into a disk swirling around the denser object. These disks glow brightly in X-rays because the material becomes superheated by the forces applied to it. Because the region producing bright X-rays is relatively small, a planet passing in front of it could block most or all of the X-rays. This is known as a transit. Astronomers have been using transits to discover exoplanets within the Milky Way using optical telescopes for many years. However, these optical light transit searches need to be extremely sensitive because the planet blocks only a tiny fraction of the light from the star. In principle, the X-ray transit technique could allow astronomers to find exoplanets at much greater distances because the X-rays can completely temporarily disappear. While this is a tantalizing result, it is not proof of the existence of an exoplanet in M51. Due to the nature of the suspected orbit, astronomers estimate they would need to wait at least 70 years for another transit to occur and confirm this current finding. Regardless, this result provides motivation for researchers to look for more of these planet candidates in other galaxies and in our own using X-rays.
Right, there you go. Back to me. Okay, we'll look at some of the ongoing projects that we're involved with now. ARIEL, or the Atmospheric Remote Sensing Infrared Exoplanet Large Survey, who thinks of these, is a European Space Agency mission. It will use spectroscopy to investigate the atmospheres of mainly hot, large exoplanets in order to understand how planets and planetary systems form and evolve. Scheduled to launch in 2028. It will be located at the Lagrangian L2 point. In fact, it won't be lonely out there, as other spacecraft are or will be out there, including the James Webb Space Telescope, Plato, which I'll mention, Euclid, WMAP, and Planck. ARIEL needs up-to-date ephemerides to ensure transits are not missed. Some of ARIEL's targets will not have been observed for many years. Their ephemerides may no longer be accurate. An example is shown on the next slide. Our involvement in ARIEL is via this Exoclock program. This is a transit light curve of HAT P6b indicating the observed and calculated mid-time varied by 24 minutes from the prediction. The current uncertainty appears to match the ARIEL requirements. That's this. This is the ARIEL requirement. That's the current uncertainty. But exoclock project measurements show a considerable deviation. These are the exoclock project measurements, thus indicating why these observations are essential to ensure the ARIEL satellite is pointing at the right exoplanet at the right time. Details of the project can be found on the Exoplanet website. These are two examples of transit light curves obtained by Martin Fowler on the left and University of Portsmouth students under the guidance of members of the Hampshire Astronomical Group on the right. And it shows the range of telescopes in use, from a 6-inch reflector operated remotely to a 24-inch reflector operated locally, one might say. Targets can be selected for your location, and if you do want to get into this, I suggest you start with deeper transits with shorter transit times, then compare your results with existing light curves. Observations can be analysed offline with the HOP software and data loaded to the Exoclock website, where it will be analysed immediately and any problems highlighted. You would be advised by email as to whether or not your observations are acceptable or if there are any problems with them. If you don't have a telescope, there are 2 online opportunities to discover exoplanets: Planet Hunters NGTS and Planet Hunters TESS. Both these use the transit method. Another way, which I just mentioned, is to use a remote telescope, in this case the Microlensing Observatory in Arizona, which Martin Fowler uses. It's free to use, and you select from available targets, as you can see on the screenshot on the left. And you download the images and analyze them with the Exoclock software. This is another one coming down the pipe: Plato, Planetary Transits and Oscillations of Stars. It's another European Space Agency mission. Its objectives are listed on this slide. Now to study both exoplanets and exoplanetary systems, in particular the properties of terrestrial planets in the habitable zone around Sun-like stars. It's scheduled to launch in 2026. This chart shows stellar mass, vertical axis, and planetary semi-major axis on the horizontal axis. Other missions, that's TESS, K2, and Cheops, will detect and characterize small planets in the habitable zone of M dwarfs, but Plato will be able to characterize planets in the habitable zone of Sun-like stars. And it's the only mission capable of doing that. There will be a Plato ground-based observation program. We've had a discussion recently, Steve Fuchs and myself and Don Polaco, as to how we might start this. There may be a pilot program starting in the new year. But it's very early days yet, and it's been delayed somewhat, this mission, by, of course, like everything else, by COVID. Right. Moving on to microlensing search for exoplanets. It's a newest project which we've been involved with. Normally light from a distant star, the source, travels to us in a straight line. However, if another star and its associated planet, the lens, pass between us and the more distant star, its gravity will deflect the light from the distant star. You'll see this as a change in brightness during the microlensing event, as you can see on this next slide. This slide shows the passage of the lens star and its orbiting exoplanet between the Earth and the source star, and the change in brightness so caused. So that's the source, this is the lens. You see it brightening. And as the planet goes across, you get another small spike. This is a typical light curve. Base magnitude is between 12 and 18, and this varies between 1 to 2 magnitudes, and an exoplanet spike may be 0.7 magnitude. So it should be well within the capabilities of a reasonable competent imager. The exoplanet spike usually lasts just over a day, so we were suggesting to images they observe daily, but now we've upped that really to every 2 to 3 hours if it's possible for them to do that. Of the 4,858 confirmed exoplanets, 164 were discovered by microlensing. Now, that's a fairly small number, but as you can see from this chart, it is increasing year by year. Listed here are the various telescope networks, projects, and space telescopes which will carry out microlensing surveys. They're not necessarily devoted 100% to exoplanet detection. More about Gaia later, as it's our source of potential microlensing targets. The Nancy Grace Roman Space Telescope is worth a special mention. It will observe exoplanets by microlensing, direct imaging, and transits, and is expected, in the words of the project website, this is a quote, to provide the most comprehensive view yet of the formation, evolution, and physical properties of planetary systems. The microlensing survey will monitor 200 million stars towards the galactic center and is expected to discover thousands of planets, both in the habitable zone and more distant. One part of the project that was missing from what the professional astronomers had was an alert process, so we've had to invent our own. This is the way it works. Coordinator, that is me. Accesses this particular website called BH-Tom. Black Hole Tom, nothing to do with black holes. It was just a fancy name to catch the eye. I then filter the targets which might be visible for northern and southern hemisphere observers. And I look at existing light curves looking for highly magnified events which have not returned to their base magnitude, hopefully to catch them when they first start to brighten. Those that look promising are then issued on an email alert. And then it's up to the observers to do their stuff and let me have the magnitudes that they've measured. This is the so-called BH-Tom website, and it lists targets in priority order. That's these red lines here. And the sky map shows the position of the targets and the sun and the moon. I then use star alt or star obs to check visibility. In this particular case, this is the object in question, Gaia 21 EFS, which is above 20 degrees, which is where you really need to observe to keep yourself out of all the horizon muck. And the moon does not rise until 4 o'clock, so it doesn't interfere with the observation. This is an example of an email alert, which I mentioned earlier. Just gives you the target, where you can find it, what its magnitude is, and you've got a link there to find the charts and other data. Do that once a fortnight, approximately. This is an example of Cambridge University Gaia Alerts data, and this was classified as a potential microlensing event. This is a fairly typical light curve, which has a base magnitude of about 15.8, but it increased by nearly 4 magnitudes. You can also get a finder chart here and links to other related data. Another useful website is Las Cumbres Observatory. Uses the same software as BH-Tom and provides very similar data. This is an example of BAA and professional observations. This was when the alert was issued, and these were all the observations that several of us made. Looks a bit mucky at the bottom here, but that was when there was a full moon, and we were using different filters. As always, filters comes into it. What we hope to do is to hold an asteroid and remote planet section workshop next year. We'll discuss how to better merge its observations and filters to use. We'll also hopefully include a tutorial on the aperture photometry tool as an alternative to Astrometrica. This chart on the right was taken from the BH-Tom website and includes both professional and amateur observations in various using various filters. But it also shows, unfortunately, that no planet was detected. So what can a microlensing event tell us? It can tell us the semi-major axis, an orbital period of a planet, the ratio of the mass of a planet to that of its host star, from which the mass of the planet can be determined, if that of the star is known, of course. So there's a lot of information you can glean from a microlensing event. The A to Z of microlensing, all you could possibly want to know is microlensing source. So why not give this a try? Your observations may help to discover an exoplanet. The presence of an unknown planet may cause variations in time or duration of the transit of the known planet. This is transit timing or transit duration variations, it's called. Notice on one of the exoclock targets, there was quite a lot of variation. And I did ask them whether this showed these timing variations might be due to an additional planet. Unfortunately, no, it has been analyzed and the answer is no. So these are just, I guess, variations in measurement, don't show a planet. Another possible project is out of transit observations. Yes, we know when the transit occurs, but if you observe for some period either side, you may detect another planet in orbit around that particular star, well described in Bruce Gary's excellent book. Another possible project is relating to TESS, the Transit and Exoplanet Survey Satellite. The TESS pixel size on the left image is quite large, and it may cover more than one star, so blending, that's called. So ground-based observations are needed to confirm whether or not a transit has been detected. This is the work of a subgroup as indicated on this diagram on the right. One of our members, David Pulley, is looking into the possibilities of us joining this program. So again, watch this space. Of course, for those of you who like long nights, there are 3, possibly 4 projects could be combined. Make a micro-lensing observation at the beginning and the start of your long night, ideally every 2 to 3 hours maybe. Image the transit targets for as long as possible before and after the known transit to look for additional planets. And observations of the transit of a particular target over a long period of time may show timing variations, which I mentioned earlier, which could also indicate the presence of another planet. So, if all this observing stuff is just too much for you, the division will try and keep you up to date with such things as astrobiology, is there life elsewhere, search for extraterrestrial intelligence, manned space flight, living off Earth, what are exoplanets made of, and anything else loosely related to exoplanets that comes our way. So we try and appeal to all sorts, not just observers. Well, I guess that's it, folks. Thanks for listening.
Many thanks, Roger. And if anyone has any questions, I see we've already had one come in, then on Zoom, if you type them in on the Q&A, and on YouTube, I'll go and keep an eye on the chat. I see we've already had a couple on there. And just while people are perhaps typing away, what I can let you know is also the next webinar, which is going to be on Wednesday, the 12th of January at 7 p.m. And that will be on observing satellites of the giant planets. And that's Mike Folks, the director of the BA Saturn, Uranus and Neptune section. And to answer Space TV, who has made some comments, we usually have these about once a month, but we also have other, when we're allowed, we have other face-to-face meetings when that's going on, and we try to stream or show recordings of those. So we've got one from earlier in December. We have a question from Darryl Dobbs. And he asks, do you think it's observational bias that more Jupiter plus size exoplanets are being discovered than Terran size planets? If it is observational bias, would this improve in time with more refined techniques and equipment, or are we unique in this solar system?
No, he's answered the question with the first part. It's easier to detect big planets, especially by transits, because they go around fairly frequently, so you're going to see a lot of planets, a lot of transits when they're close to the star, and being large, the transit is quite large. If you've got a small planet a long way away, it's hard to detect, and you might only see it once in the proverbial blue moon. Yeah, things are getting better, and as mentioned earlier, things like the Nancy Grace Roman telescope, James Webb, and the other satellites I've mentioned will make life a lot easier. But yeah, it's much easier to detect something big close to the star than it is something small a long way from the star. Especially if you're talking about radial velocity, because a large planet close to the star will show up on spectroscopy, whereas a small one won't shift the host star that much.
And then we have a comment from Darryl Dobbs, which is, I think there's a project on exoplanets on Zooniverse.
Yeah, one of those I think mentioned was on Zooniverse. I can't remember which one it was, but there were a couple. But I think one of the two I mentioned is on Zooniverse. Yeah.
And a comment from John Fairweather is, it is called TESS. It replaced the one called Kepler. Yeah,
Kepler, I think, has met its maker. I think even the K2 version, yes. But TESS is certainly working hard, detecting lots of planets. But again, it needs confirmation because its pixel size is quite large, and you can get what you call blending. That's two stars on the same pixel. So again, ground observation is key to deciding whether it's really a transit or not.
And then we have another comment on YouTube from Space TV, and that's a question. And that's, what is the current situation with detection of exomoons? Weren't there a couple of false positives?
Yeah, something I looked at a little while ago. I think there are about 6 or 7 possibilities, and no, none as yet.
Yeah, so watch that space. And no more questions coming in. Okay, and here on YouTube again from Space TV, he asks, what does Roger personally think is the most interesting mystery about exoplanets that he would like to solve one day?
Well, there's only one mystery, and that's, is there anybody else out there? That's the question. Well, that's the answer. Is it the question?
And to answer Space TV's other question, which I'm not quite sure if I got to earlier, but yeah, we have all of these videos on our YouTube channel, so you can always link to our YouTube channel if you want to from your website, or to individual videos.
Space TV. Okay.
So that's the name of the person who's commenting on YouTube. And I think at the moment that looks like it for the questions.
Jolly good.
So it could be a nice snappy one. Oh, here we have one from Alex B, who's asking, which exoplanet found so far looks like the best potential for life?
I can't name that off the top of my head. So there's only one possibility so far, and possibly 5. If you go on Wikipedia and look that up, there's a list of them. Or if you go on the Exoplanet EU website, there's 2 or 3. There's Exoplanet EU, and there's a NASA website as well, and they will list them. But no, there was only one possibility so far, and I can't remember off the top of my head what that was.
And I think the trick, a bit like with the others, is going to be confirming it, because it's yeah, we kind of limited information we can gather at the moment, though James Webb may help once that launches.
Yeah, I think that the problem's going to be, I mean, there may be life, for example, on some of the moons of our own solar system, and sooner or later we'll be able to send robots there, or even go there ourselves. The big problem with exoplanets is, of course, it's such a long way away that unless we get somebody, an ET waving at us, it's going to be an awful long time before we get to any of these exoplanets. I think that future generations may find that a bit of a problem, and they may get frustrated that they can't actually get any further. They may be able to detect, for example, biosignatures, as I mentioned, in the atmospheres, But to be absolutely sure, you're going to have to go there. Won't be in your lifetime or mine.
Yes. Long way off. Great. Well, thanks very much, Roger, for taking the time to present to us tonight on exoplanets and the work of the Exoplanet Division.
Jolly good.
This recording, along with our others, available on the YouTube channel, so please feel free to watch any which you want. And look forward to seeing many of you in a month when we have Mike Folks talking on the satellites of the giant planets.
Oh,
Thanks
thanks for
all.
listening, folks. So you know where I am if you want to ask any more questions anyway.
And wishing everyone a happy and safe holiday season.
Yep. Merry Christmas and a Happy New Year. Bye.